Hello and howdy, ladies and gentlemen, one and all, welcome back. We're going to be finishing off the 2014 Canadian Open paper in this very video. So if you haven't given C4, the last question, a try, I would strongly encourage you to do so. Here is C4. So if you want to pause the video, read it, try, even just trying A or something like that, just to get a taste for the question, that would be perfectly fine. Okay, so let's read here. So C4. A polynomial f of x with real coefficients is said to be a sum of squares if there are polynomials p1, p2, pn, n is some number, with real coefficients for which f of x is p1 squared plus p2 squared plus all the way up to pn squared. So it's sort of like a sum of squares for integers, and so integers can always be written as a sum of 4 squares, which is kind of interesting. We might show something similar. We might rely on that fact, although I don't think we have to rely on that fact because it's not a very well-known thing about integers. But yep, every positive integer can be written as a sum of at most 4 squares. Kind of nifty. Alright, so for example, 2x to the 4 plus 6x squared minus 4x plus 5 is a sum of squares because we can break it down as x squared squared plus x squared plus 1 squared plus 2x minus 1 squared plus root 3 squared. Something to, I think, note right off the bat, just before we actually dive in, I think you can show that if f of x is a sum of squares, then the highest degree of x must be even. Okay? I'm fairly certain that we should be able to show that. I always like, when I read these questions, to think, okay, what can I say, what's jumping out at me, what can I immediately recognize before I even get into the question. So, just sharing that with you. I think the degree has to be even of f of x. And that might be a complete characterization, or maybe that's a stepping stone to building something up. Who knows? Okay, so what have we got here? A. Determine all values of a for which x squared plus 4x plus a is a sum of squares. Okay. Well, part of this already looks like a square, so this doesn't seem not doable. Seems perfectly reasonable. I'm going to read B and C now just to sort of get a sense of where the rest of the question is going. B, determine all values of a for which x to the 4 plus 2x cubed plus a minus 7x squared plus 4 minus 2ax plus a is a sum of squares. And for such values of a, write f of x as a sum of squares. Okay. And C, suppose that f is a sum of squares. Prove there are polynomials u of x, v of x with real coefficients so that f of x is u squared plus v squared. So I guess what C is saying is that if you're a polynomial and you're a sum of squares, then at most you're a sum of 2 squares. And that's a little different from the positive integer case, but there's probably a little more flexibility there. So, I'm not quite sure where to go with C. Maybe some sort of factoring with irreducible quadratics or something to that effect. We'll see. But I suppose we could say, all right, let's get to A. So we obviously need a linear term. And so f of x plus x squared plus 4x plus a. You're not just going to get away with just single constant squareds. You're going to need at least one linear term, right? So this has to be cx plus d squared plus some other stuff, some other squares. Okay. But then we get cx squared plus 2cdx plus d squared. Actually, I think it's easier just to say, well, obviously I can peel off a square. Then I'm wondering. It'd be plus 2. I'm wondering, is this the only only way to do it? Like, is it possible there are other squares out there that you know, going to cause us other problems? And things to think about. All right, so x squared. Well, let's say notice x squared plus 4x plus 4 is equal to x plus 2 squared. So, a being equal to 4 would certainly work. Actually, because they had a root 3, didn't they? Yeah, they had this root 3 squared, so we should be able to do it for so let a be greater than or equal to 4. Then 4 minus a is... Sorry, then a minus 4 is less than or equal to 0. It's greater than or equal to 0. So we can write f of x is x plus 2 squared plus the square root of a minus 4, whatever it is, squared. What about a's that are less than that? Well, a's that are less than that. Wait, no. So if I were to graph this, depends on a. Now, if a were 4, we'd get double root right here. Now, a also increasing a brings it up higher. Decreasing a brings it lower. So if a were something like 3, we'd get roots at -1, -3, and we'd get what do I want to say? Vertex down here. So let's say if a is less than 4, and we see f of x is equal to x plus 2 squared plus a minus 4. And so f of -2 is equal to a minus 4, which is less than 0, because a is less than 4. But if f of x is equal to p1x squared plus all the way up to pnx squared, then f at -2 should be p1 -2 squared plus all the way up to pn -2 squared. But a sum of squares, and these are just squares of real numbers now. Plug in -2 in for x, you can evaluate, you get a real number. But a sum of squares is always non-negative. So only for a greater than or equal to 4 will we get f of x as a sum of squares. And it turned out to be 2 squares. So that's kind of nifty. Alright, now b involves a quartic, so it should be a little harder. We got x to the 4, 2x cubed plus a minus 7x squared plus 4 minus 2ax plus a. Well, again, we might think about plugging in certain values. Like, if I plug in x equals 0, the only thing that's left is a, so a definitely has to be positive, so might we get sort of a range of inequalities and then certain cases as to how to break things down? Certainly certainly possible. I think once again, knowing that we've got this x to the 4 plus 2x cubed up front makes me think that maybe we should sort of go with an obvious square and take that away and see what's left. I'm a little wary, just like I was in A, because how do you know that you can't get a sum of squares some other way? And that's what I'm worried about. But it worked out in A, so let's take a look. So for B, consider x to the 4 plus 2x cubed plus x squared, which is x squared times x plus 1 squared, which is x times x plus 1 squared, which I guess we should just write as x squared plus x all squared. Alright, then we can write f of x is equal to x squared plus x squared plus, and then what's left over? So we borrowed an x squared, so now it would be a minus 8 x squared, I think. Yeah, borrow to take away an x squared there. So I had to peel one off to come join this part. And then plus 4 minus ax plus a. Okay. Now, could we take out an a minus 8 factor or something like that? Or actually, I'll tell you what, could we borrow another x squared and a? Tricky. Well, what do we say? Ax squared minus 8x squared. I don't like this minus 8x squared bit here. Plus 4x minus ax plus a. If we pulled out another x squared, we could group it with the 4x plus a, and oops, we need a minus a in there. Minus ax plus a. So that'd be x squared plus x squared plus x plus 2 squared plus a minus 4 square root squared. And then what would be left with? A minus 9 x squared minus ax. Ooh, I don't like that. No, I do not like that. Maybe it was a mistake. Let's go back and just look at when I take off the obvious square. It's something like this. Now, if I were to plug in a value like x equals 0, so this needs f at x needs to be f at 0 needs to be non-negative. So a definitely has to be greater than or equal to 0. Maybe it is just going to be inequality work. What if I tried f at negative 1? Because then this is going to be 0. A minus 8, and then we get 1, plus 4 minus a, negative 1, plus a, and so we have a minus 8 minus 4 plus a plus a, which is 3a minus 12. So 3a minus 12 has to be greater than or equal to 0. So a has to be greater than or equal to 4. So is it enough just to have a greater than or equal to 4 again? I can't think of any other obvious values to plug in. Maybe 1. Let's try f at 1. So f at 1 would be, you get 2 squared plus a minus 8 plus 4 minus a plus a. So that'll be 4 plus a minus 8 plus 4 minus a plus a. Those cancel, those cancel. So once again, we just get a has to be greater than or equal to 0. So nothing particularly insightful there. I don't want to keep messing around with numbers if I can help it. I mean, if I'm really stuck, maybe I'll try like 2 or something, but... so sum of squares, and for such values of a, write f of x as a sum of squares. Okay. So I know a has to be greater than or equal to 4. This is definitely true. And I like that we're using this property again. So if a is greater than or equal to 4, 4 minus a is less than 0. So I guess, could we get a negative squared somewhere? So yeah, so try x minus 2 plus a over 2. So square that, you get x squared plus 4 minus a. No, I've done something wrong there. Plus minus a over 2 minus 2. Let's say that. Because then the negative 2 gets doubled to a 4, and the a over 2 gets doubled to an a. Okay. I get a over 2 minus 2 squared, which I'm not the most enthusiastic about simplifying, but then there's that. So f of x would be x squared plus x squared, plus now a minus 9x squared, plus this thing, plus a, and then minus this square that had to be added in. So minus a over 4 plus 2a minus 4. And this is a 9, not an a. Well, again, I'm not entirely happy with what we've done, so I'm starting to think maybe we should go back and re-examine the choice of f of x. Or not choice of f of x, but the choice of the first thing we split off from f of x. But it seems so natural. X squared, the 2x cubed. A minus 7 seems out of place, and the... Oh, did I do a typo again? 4 minus 2a. Oh, God, I hate when I do this. I always do this at the 2a. How long have I had that typo in there? Basically the whole time. I should have checked. I should have double checked. Okay, starting a new fresh sheet. Let's try f of x, and now let's write it down properly this time. Four minus 2ax plus a. Now this could change things with some of our work, we might not necessarily need a greater than or equal to 4 or anything. A minus 7, 4 minus 2a, not 4 minus a. So once again, if we were to plug in 0, we'd be fine. What if we plugged in 1 again? Actually, let's do negative 1 first. To see if... so... Now, negative 1 was only really useful to plug in when we had peeled off that first bit, and I'm not happy with that, so we're trying something else. Let's just try f at 1. 1 plus 2 plus a minus 7 plus 4 minus 2a plus a, and oh! The constants cancel. A minus 2a and an a, they cancel as well, so we get 0. Okay. So we actually managed to find a root. That's kind of unexpected. Now, the whole time I've been trying to split off sums, but like split it, like have this sum or this square plus this square plus this square, so sums. But what if we could peel out a square? Because if I could write this, if I could write f of x as a polynomial squared times a smaller thing, and show that this is a polynomial squared plus a polynomial squared plus maybe another polynomial squared, then we could just multiply through and get f as a sum of squares. So that might be a legitimate strategy, peeling out factors and things like that. That might even be a way to approach it for C. We'll see. Okay, so I guess what we could say, well, I can't guarantee it yet. We know 1 is a root. We don't necessarily know it's a double root or anything like that. But so 1 is a root of f of x. So I guess if we did some polynomial division, we get x to the 4 plus 2x cubed plus a minus 7 x squared plus 4 minus 2a. This video is going to be like 5-10 minutes longer just because I did not see that 2 there or forgot about it. Alright, x cubed, x to the 4 minus x cubed. So 3x cubed, so plus 3x squared minus x squared, a minus 7x squared. So that would be a minus 4x squared. Bring down the 4 minus 2ax. We'll get an a minus 4x. Don't need to write that. A minus 4x, so it would be negative a minus 4x. So 4 minus minus 4 is 8. Negative 2a minus 2a is minus 3a. Ooh, don't like that. And then plus a. Something's up. All right, minus 4. Minus 4. So yes, it should be minus 4, but then we subtract that, and so it'll be 4 minus 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 4, which happens to be nothing, and negative 2 minus minus a, which is negative 2 plus a, so it should just be a minus x. And so we should get a minus a, and then we'll get everything we need. So it works out. So f of x is x minus 1. Now, cross your fingers. I suspect this should be true just because this would be really nice. Let's make sure we copy it right this time. A minus 4x plus a. No, minus a. Well, I'm liking that the a's will cancel out. We could just add up the coefficients, but I think it'd be a lot more fun to just plug it in. 1 cubed plus 3 1 squared plus a minus 4 minus a, those will cancel. 3 and 1 make 4, cancels with the negative 4. So we can get another root here. And we'll be back at a quadratic, which are nicer to handle. It's really nice handling quadratics. Just thinking ahead for C part, I think we could probably, using our parabola, finding the vertex and letting the vertex be as lie right on the x-axis might give us ways to show how to make, putting parabolas in vertex form, I think can make sure quadratic expressions are sums of squares. So that might be something to build off of with, what am I thinking of? Part C. Just thinking ahead to part C. Anyway, x squared, x cubed minus x squared, so this will be 4x squared, so it'll be plus 4x. So plus a minus 4x, we'll get minus 4x, and it'll be minus 4x, so this will be a x, so we'll get plus a, and everything will work out there. And that's the one from part A. That is the one from part A, unless I'm misreading something again, but no, we're good. Okay. So, what shall we say? Well, I claim f of x is a sum of squares exactly when x squared plus 4x plus a is, i.e. a greater than or equal to 4. So how would we prove that? If a is less than 4, then as seen in A, negative 2x squared plus 4 times negative 2 plus a is less than 0. So f of negative 2 is negative 2 minus 1 squared times, I don't know, let's call it k, where k is less than 0. So that's 9k, also less than 0. Therefore, f of x not a sum of squares. Now, have I actually codified this rule? Yeah, I sort of made reference to it here. If f is a sum of squares, then x... well, let's write it down just so that we have it nice and neat, in case we want to use it in C. If f of x is a sum of squares, then for all real r, f at r is a sum is p1r squared plus pnr squared, and therefore greater than or equal to 0. So that's the rule we've been using a couple times. Alright, so if a is less than 4, then we don't get a sum of squares. If a greater than or equal to 4, then x squared plus 4x plus a is equal to x plus 2 squared plus square root of 4 minus a. No, x minus 4. Got the order there wrong. Oh, you know what? Writing all that a minus 4, 4 minus a might be why I miscopied. And so f of x is equal to x minus 1 squared times this squared which should be equal, we'll put the big squarey brackets there. X minus 1 times x minus 2 is x squared plus x minus 2. And then we'll have root a minus 4x minus root a minus 4 squared. So there we go. Not only have we figured out what values for a, f of x can be written as a sum of squares, but we actually finished off b by actually showing them what the sum of squares would look like. And once again, we have two squares. Kind of interesting. Okay. So, C part. Suppose we got a sum of squares. Show that it can be just a sum of two squares. Okay. So, what can we do? Well, let's see here. I think, so I like the idea of factoring out, but we can't always be guaranteed that there's going to be a double root, that there's the x minus 1 squared that can pop out. But if the degree is high enough, if the degree of f of x is greater than or equal to 2, you can always pull a quadratic out. And so, factoring out a quadratic, because we just care about real coefficients, they don't have to be integer coefficients or rational coefficients, so you can always do that. There's always either two real roots or an irreducible quadratic that you can pull out. And so, yeah, we should be able to, and that would pull the degree of f of x down by 2. So we might be able to induct on the degree. So first, let us say if f of x has degree 0, that is to say, then f is a constant. And if it is a sum of squares, then f of x is equal to f at any value. So f at x is equal to 0. So we could just write it's the square root of f at 0 squared plus 0 squared. Okay? So now, I don't think, so f of x, let's say, can't have degree 1, since if f of x equals, let's say, ax plus b, then it isn't a sum of squares of constant polynomials. But any sum of linear polynomials, polynomials of degree 1, well, let's say it this way. Well, actually, no. If f of x were linear, no, that's silly. I can just say actually, this is why you can't be odd, because so f of x can't have degree 1. Actually, let's just say f of x can't have odd degree. As any odd degree polynomial has a root and crosses the x-axis. So for example, every linear term either looks something like this or like this, and you're going to get some negative values. Any cubic looks roughly like this or like this. It crosses the x-axis, you're going to get some negative values. So f of x will take on some negative values. But that can't happen because we had this earlier rule that we wrote down. We might even call it star because we refer to it so many times, so we could say it can't have negative values by star. And we could have referred to star earlier in A and B as well, as long as we wrote it down. And that sort of underlines the idea of doing some rough work. If you do rough work, you say, this is a nice important result that I use a lot. Let me put that right at the top and give it a fancy name like star or lemma or something like that. And so that way you can keep referring to it. And it also makes you seem kind of fancy. Okay. So, what else can we do here? So we can't have negative. So that means, so therefore f of x has even degree. Now, any polynomial with real coefficients that has degree greater than or equal to 2 has either 2 roots, not necessarily distinct, or has a factor of an irreducible quadratic. Okay, this comes from the fundamental theorem of algebra, which you may have encountered if you've learned complex numbers at all. Okay. Fundamental theorem of algebra basically, there's lots of different forms of it, but basically it says that either, so that you can always keep removing factors that either are linear, like an x minus r sort of thing. You can keep pulling out single roots, or you can pull out an irreducible quadratic. So, what am I trying to say? Basically what I'm trying to say is I can pull out a factor that is quadratic. I don't care if it's irreducible or not. But that's the point. So it has either 2 real roots, either at least. So what we're really saying is thus there is a quadratic. I was almost about to say irreducible. It doesn't have to be irreducible. There is a quadratic. Let's call it q of x. So f of x equals q of x times, I don't know, I don't want to use p of x because that should be before. So let's call it r of x, I guess. Nah, s of x. I feel like s of x. Okay, so we get r of x q of x times s of x. And s of x has degree equal to the degree of f minus 2, because we took out degree 2 polynomial. Now, q of x isn't necessarily this x minus 1 squared type of stuff, so it isn't necessarily a square, but I'm willing to bet we can turn it into a sum of squares, since f of x is a square. So we'll prove by induction on the degree of f of x that it can be written as a sum of two polynomials squared. We saw if degree f equals 0, this is true. Okay, that was our base case. We wrote that down a long time ago. Here it is. So you might even want to instead rewrite it over here, or where we are now, or put a nice colored box around it, but that's our base case. So we already handled that. So now we can assume that Sx, well actually no, hold on, how do we know Sx would be a sum of squares? Ooh, that might be a problem. That might be a problem trying to show that Sx is also a sum of squares. But if it was, then I think we could probably manage to show that f of x is a sum of squares. Actually, I wonder if we could prove a stronger result. So we'll prove by, I'll see if this will work. This might be too strong and therefore won't work, but no reason not to try. So we'll prove by induction on the degree of f of x that if fr is greater than or equal to 0 for all real r, then f of x is the sum of two polynomials squared. So this is true for the degree of f of x. We already showed that. We're just making the assumption that f of x is greater than or equal to 0, and then we showed that it's the sum of two things. But then, okay, so here's our induction hypothesis. Assume it is true for polynomials of degree less than the degree of f. So as remarked, degree of f is as remarked, we can write f of x is a quadratic times s of x. So suppose s at r is less than 0. For some r. And what I want to do is show that s also has to be positive. And well, f at r is greater than or equal to 0, so q at r must be equal to 0. Or no, I suppose q at r could be less than 0 as well. So maybe it can't be done this way. Well, that doesn't necessarily mean that the QX idea is wrong. Well, okay, let's think about this. Q of x either looks like a double root or two single roots, or is irreducible. Now, if so, this either looks like a double root like this, two separate roots, or something that lies completely above or below the x-axis. So this one, just like we saw in A, will be expressible as a sum of two squares. This one's always positive, but there's a chance that there's sort of this s function that also dips below exactly when QR does. Or that it's that s is only negative when q is 0. So I suppose we could handle these two situations. Or these three situations. So, cases. Q of x equals x minus r squared. Then SR is only place that s of x can be less than 0, but Sx is a polynomial, and so it's continuous. That is, I can draw it without lifting my pen from the page, so it can't just jump down to be negative. So in that case, SR is always greater than or equal to 0. Okay, because it can't be negative once. And still, so there's no way to draw a function that stays up here, then suddenly jumps down here, and then is back up here, because I lifted my pen from the page. Okay? A little bit of reasoning. I mean, if you take a more advanced class, advanced math class in university, they'll talk more about what continuity really means, but definition fits fine here. Let's suppose q of x is equals x minus r1, x minus r2 times some a, and a is going to have to be positive. Because otherwise I could just change the sign of q and make s also change sign as well. Then Sx can only possibly be negative between R1 and R2. Okay, so why shouldn't that happen? Well, again, Sx is continuous. So if it is greater than or equal to 0 for an x before R1, and S of x is less than 0 at some x in between R1 and R2, if it actually ever is negative, then it needs to cross the axis at some point. And x has a root before R1, at R1, or after R1. Likewise, a root before R2, at R2, or after R2. we can pick Q. So let's say f of x only has so many real roots. It only has a finite number of real roots. Pick Q of x so that no other roots of f of x are between the roots of Q. Okay, so if that's the case, then we conclude Sx has a root either at R1 or R2. Because it can't have a root before R1 and R2, because imagine what that would look like. Here's your Q of x. Now we know that over here, S of x has to be non-negative, right? We know that has to happen. I mean, I suppose it could be 0. It's not going to be 0 infinitely often, because it would only be 0 at so many roots. So it's going to be positive somewhere. And we're saying that maybe S of x is negative somewhere, but if it is, it's got to be somewhere in here to cancel out the negativeness of Q of x, right? Okay, but then there's some root of S of x. Maybe it's beforehand, but then S of x is negative a little bit beforehand, and so there's this nice little area here where the Q value is positive, the S value is negative, so the F value would be negative. So that can't happen. So maybe it happens afterwards, but then there's this. Well, then there's this root here that's between the two roots of Q, and we just said that shouldn't happen. So it has to happen at R1 or R2. In fact, it should happen at both of them. So let's say SR1 is equal to 0. Then R1 is a double root of f of x. So let f of x be x minus R1 squared times some new s of x. And go back to case 1. And by case 1, this s prime will always be non-negative. Finally, case qx is irreducible. Then q of x has to be greater than or equal to 0 for all x. So then s of x must be greater than or equal to 0 for all x. Actually, q of x has to be greater than 0. Otherwise, f of x will be negative at some point. If s of x is negative at some point, f of x will be negative, because you're only ever multiplying by q of x, which is always going to be a positive value. Okay, great. So, if the reasoning works out, then f of x is equal to q of x times s of x. So now, by induction, s of x is a sum of 2 squares. Great. Okay. Not only that, but can't we also use this reasoning to conclude that yeah. So I think we can reword this second case argument to say that you can always rearrange f of x equals x minus r squared and then another s prime of x. Actually, let's rewrite that now. So, what exactly do I want to say here? Okay, s of x must have a root at x minus a root at r1. Here's our reason why. Sx is less than 0 between r1x and r2x. Well, it's f of x has finitely many zeros. So must s of x. So sx is negative for some x. Not necessarily all of them. There are times it could be 0, but there's some x after r1 where it's negative. To balance q of x, which is always negative for all x in this range. Okay? Sometimes x of x could be 0, and so they multiply together and f of x is 0. But other times s of x has to be negative because qx is always negative in this range. Similarly, s of x has to be positive for some x before r1 to balance q of x, which is positive before r1 and after r2. Okay. So, s of x, if s of x is, no, actually, this might be a better argument, and something that I might not have to cram in as much. I'm definitely writing small because I only give myself so much room to rewrite. So let's instead say this. If s of r1 is greater than 0, then since it's continuous, it can't immediately jump to 0 or negative. It is greater than 0 for a little after r1, and so sx qx would then be negative, since sx is positive and qx is negative a little after r1. Similarly, we can't have s at r1 be negative, because then it's negative a little before and s of x, q of x would then be negative as well, because qx before r1 is positive, and then sx we're saying is a little bit negative. Okay? Because I can't say, here's my r1, I can't say, well, Sx is negative here, but then suddenly jumps up to 0 or positive just beforehand. That's not how a continuous function works. That's a jump. I can't draw that without removing my pen from the page. So that's a better argument. So now we can say S is the sum of two squares, and f of x either equals a times x minus r squared s of x, or some irreducible quadratic. Okay. So, a greater than 0, and q of x always greater than 0. All right, we're closing in here. I might call this case 1, case 2. So for case 1, f of x is equal to a, x minus r, x, and we can say this is u squared plus v squared. And so this is root a, x minus r, uv squared, and then root a, and v of x squared. Case 2 is a little trickier. Let's say put q of x in vertex form. So both a and k are positive. That way we never get 0. And we're always above the axis. Then q of x can be written as root a x minus h squared plus root k squared. And then f of x can be written as u squared x plus v squared x coming from the qx times w squared x plus x, ooh, don't want to use that, let's say t squared x. Let's say t squared, u squared, v squared, w squared x. Okay, now this product, can I make this into a single square? So I feel like we can if we're clever. So we get, I'm going to drop the of x's just because I'm trying to work this out. TV, TW, UV, UW. So we want to have that. This is a nice trick. Group pairs that have nothing in common. And so this should be, we'll leave this up here just to double check, but we should be able to do TV minus UW squared plus TW plus UV squared. So if I do that, that's T squared V squared minus 2 TUVW plus U squared W squared plus T squared W squared plus 2 TUVW plus U squared V squared, and those guys in the middle cancel. Yeah. That's a trick. It comes up every once in a while. I've seen that before when I think dealing with products of primes that are congruent to 1 mod 4. I think there's even a similar multiplication you do when you actually prove that every integer can be written as the sum of 4 squares. I don't remember exactly what that one would be. That would be huge and terrifying. But weird factorizations like this, they come in handy, clearly. So let's say this is Tx Vx minus U x Wx squared plus txwx plus uxvx squared, which concludes the result. Alright, so that took a while. My induction idea took a lot of revising. I'm sure if you just took this as rough work, you could write it a lot nicer and neater, especially my little continuity argument here that allows me to just pull out a double root, which really simplifies the cases at the end. But, yeah, not overall too bad. Showing that you can't have odd degree, that's pretty nice. The base case is good. The induction hypothesis, then we showed everything works out. Now, the induction hypothesis was a little weird, and we also proved something stronger. So I guess this is a complete characterization. So now I actually know whenever you can write as a sum of squares, you just have to always be non-negative in your values. If you can do that, then you can be written as a sum of polynomial squares. And that's kind of cool. We actually proved a stronger result, which isn't always possible. That's kind of nifty. We learned a little bit more about polynomials. So that was C4, and that finishes off the whole... Oh gosh, what year was this? 2014, right? Let me just double check. Yeah, 2014. All right, I don't know. I've been recording a lot of these. But, okay, so that's the 2014 Open. I guess up next we'll be looking at the 2015 Open paper. Hopefully many good questions there. I liked some of the questions on this paper. And if you're looking for other math contests, feel free to browse around the channel. If you had a different way of doing the question, especially C part, you know, if you didn't even use an induction, I would love to hear about that. You can leave a comment down below. Feel free to subscribe if you want to be kept up to date, share it around. I like, you know, some people have said they've shown other people in there who are at their school who are good at math, these sorts of things. And so, you know, it spreads around, and I just want this to be a resource where people can learn different ways to do contests, how to think through contests, and the general approach. You know, just keep having fun doing math contests. So I will see you for more math in whatever video you manage to watch next. Take care.